Welcome back. And in the first video in this series we looked at Le Chatelier's principle. We're going to move on this time and look at Gibbs free energy, and we're also going to start looking at Kc. That's the equilibrium constant. So you're going to need your notes and a calculator, and we're on page 10. So we're on page 10 of your notes and we're looking at this equilibrium which we studied earlier. So NO2 is a brown gas and N2O4 is colourless. Now if I started with pure NO2 and I allowed it to reach equilibrium, I would get significant quantities of N2O4 and vice versa. So we need to think about the feasibility of these reactions. And this is where a Gibbs energy plot comes into play. We should remember from our entropy notes that if delta G, the change in Gibbs, is negative, we say the reaction is feasible. Any reaction that results in a negative delta G value will work, will go, and anything which has a positive delta G value will not. So here I have pure reactants. So this is 100% reactants, no products. Here I have 100% products and no reactants. Well, you can see that the products moving in this direction, changing composition in this direction, is going to give you a negative delta G, because the change from this composition to this composition would be a negative G. Likewise, if I change from pure reactants to some products and some reactants, that again is a negative delta G value. Eventually I'll come to this point here, this composition. At this point, any changes from this point would result in a positive delta G. If I tried to move from here more towards the product side, that change from that composition to this composition would be a positive delta G, and that would be non-feasible. So we can see the same thing on this plot for the Haber process at the bottom of the page. So on this side I have pure nitrogen and hydrogen, and here I have pure ammonia. So any changes from pure ammonia towards nitrogen and hydrogen is going to be a spontaneous reaction, because that's going to be a negative delta G value, and likewise this is also going to be a negative delta G value. At some point they're going to come to an equilibrium, and the equilibrium is always at the minimum, and at this point my delta G equals 0. In other words, I have no change in G, and that's another way of defining equilibrium, where the change in G is 0. The other thing you can see on this plot is this capital K. This is my equilibrium constant, and at equilibrium it equals the ratio of the products to the reactants. Skipping over the next 2 pages, which is the practical we'll do in class, we're now on page 13 of your notes, and we're going to introduce this idea of an equilibrium constant, capital K, and because in this version we're looking at concentrations, we put a little c after it. So we have our equation here, A plus B going to C plus D. The small letters here represent the balanced stoichiometry of the equation. So the Kc is equal to the concentration of C, that's one of our products, times the concentration of D, all at equilibrium, and all raised to the powers in the balanced stoichiometric equation. So it's important you always quote an equation so we understand our expression. Couple of things you need to remember about these Kc expressions. They are not affected by pressure or by concentration. They are only affected by temperature. And because we're dealing with concentrations, we do not include solids or solvents. We don't include solids because their concentration is not going to change. Likewise, if we have a solvent, again, its concentration is not going to change throughout the reaction. So we're going to have some goes at doing some examples of writing out Kc expressions, and then we're also going to look at units. So the first example we have is hydrogen gas and bromine gas reacting reversibly to form hydrogen bromide gas. So I can write my Kc expression for this, and it is equal to the concentration, so I'm going to use square brackets because that's what stands for concentration, of hydrogen bromide, and that's going to be squared because I've got 2 there in my balanced stoichiometric equation, divided by the concentration of hydrogen times the concentration of my bromine. Those are both raised to the power 1, but we don't generally include those. Now, because the equilibrium constant is based on an individual stoichiometric equation, the units are going to be different each time, and we always need to work out and include units. Now, in this case, I have concentration squared on the top divided by concentration times concentration. So those units will all cancel. One way of working this out is to let big M stand for concentration. So we have M squared divided by M times M. So that cancels and we have no units. Our second example on this sheet was nitrogen gas and hydrogen, H2 gas, reacting reversibly to form ammonia. And under the conditions we're going to do this, that is also going to be a gas. Again, we can write our Kc expression. That is the concentration of the ammonia, NH3, and that's going to be squared, divided by the concentration of the nitrogen, raised to the power 1, times the concentration of the hydrogen, cubed in this case. So that's our expression. But what we now need to do is we need to work out the units. So again, using m's, I've got m squared divided by m times m cubed. Now that simplifies to 1 over m squared, because I've got 4 on the bottom, 2 on the top, so it cancels down to this value, or m to the minus 2. So bring that m up to the top. Now, I can't leave it like that because m is not actually the unit, so I need the real units for concentration. The units for concentration are moles per decimeter cubed. So this becomes moles dm to the minus 3 all squared, also minus 2, minus there. So that becomes moles minus 2 dm to the 6. Those are my units. So you always need to work out units. You'll always get a mark for this working out of the units. You don't need to use m's. You can go straight to use moles per decimeter cubed if you want to. I just do it this way just because it's easier to cancel it down and then rewrite it. But it's totally up to you how you work out the units. And you can see how we've done those at the bottom of the page. So again, we need to have our balanced stoichiometric, and our Kc is the concentration at equilibrium. Quite often we drop this subscript EQM, but we need to understand this is not the concentration at the start, it's the concentration once equilibrium has been reached. So we're on page 15 and we're going to look at some of these calculations. So the first thing I'm going to do is I'm going to write my expression for Kc for this equation. This is again the Haber process, so it's nice and straightforward. You just need to practice doing these so they become almost second nature. Don't forget to use square brackets because the square brackets stand for concentration. So there is my value. Now what I'm going to do is I'm going to use the data in the table, which is the equilibrium concentrations, to calculate a value for Kc. And I've put my numbers in and I've given my answer to 3 sig figs. The reason I've given my answer to 3 sig figs is my data is given to 3 sig figs. And again, I always remember to include units. And again, I've got 1 over the concentration squared, so that becomes moles to the minus 2 dm6. You should normally write it actually as dm to the power 6 moles to the minus 2, but that is perfectly acceptable. So on to the next question. We're looking at the reaction between hydrogen and sulfur to form hydrogen sulfide. Again, we're going to write out our Kc expression. Again, notice that the H2S is squared, as is the hydrogen, and we've worked out our units. This time, we're asked to work out what the equilibrium concentration of the sulfur is. We've been given our value for Kc and we've given our values for hydrogen and hydrogen sulfide. So it's just a case of putting it in the equation, rearranging it to find the concentration of the S2. And this last reaction is looking at a redox reaction between tin and iron. And again, we're going to write our Kc expression. In this case, the units cancel because you've got the same value concentration terms on the top as on the bottom. So we're now asked what the value for Kc is for the reverse reaction. This is one of the reasons why you always need to specify the equation. Now, if it's 10 to the 10 going forwards, going backwards, it's going to be 10 to the minus 10. Because if you like, all that's happened is this equation has been flipped over. So it's 1 over that 10 to the 10. So that's 10 to the minus 10. And likewise, if I went through and doubled everything, that would be squared. Likewise, if I go through and I halve everything, so I've got half, 1, a half, and 1 there, it would be the square root of my original Kc value. So it would be the square root of 10 raised to the power 10. So that finishes off today's video, just looking at the basics of Kc and relating it to Gibbs free energy. In the last video in this pack, we're going to be going on and looking at calculating Kc from first principles. So until then, take care, stay safe, bye bye.